Hello everyone, I'm Sahab Azmi and today I will be presenting my survey titled A Comprehensive Survey of Large Language Model for Earth Observation Data Description. Uh, this paper explores how LLM large language models are being used to analyze and describe Earth observation data sets, such as satellite images, climate records, and remote sensing data. Over the last few years, the geospatial community has seen a major shift from conventional image analysis methods that rely heavily on handcrafted features to AI models that can understand spatial and semantic patterns automatically. In this presentation, I will explain how LLMs are applied to generate image captions, perform spatial reasoning, and even act as intelligent agents capable of answering natural language questions about our planet. Essentially, this survey shows how AI is moving from being just a tool to becoming a true collaborator in understanding Earth system. Now moving to the next slide. This in this slides we will talk about motivation and scope. So the motivation behind this work stem from a fundamental challenge in geospatial science. Earth observation data is massive and complex. We collect terabytes of data daily from satellites, drone and sensors. Yet most of it remains underused because interpreting it manually is slow and expensive. So traditional machine learning techniques are good at detection and classification, but they struggle to communicate results in human understandable language. So that's where LLM come in. They can bridge this gap by converting data into meaningful descriptions, insights, or even policy relevant information. This survey scope covers how LLMs and MLLMs, multimodal that understand both images and text, are transforming remote sensing through automated captioning, localized understanding, and interactive agents. So, the main goal was to organize the existing research landscape and highlight both progress and current challenges. So, our review centers on three transformative tasks. The first is automated descriptive captioning, where LLMs are trained to describe satellite images in natural language, for instance, an under area with dense road networks and industrial structures. The second is object detection and contextual characterization. Here, LLMs and vision models identify specific features such as vehicle, farmlands, or rivers and explain their spatial relationship. And the third task is LLM powered agents, which take one step further. These agents can respond to natural queries like show me a deforestation in Brazil between 2010 and 2020. The retrieve and visualize that automatically. So together these areas represent the frontier of geospatial AI research. In this slides, we will discuss about RSIC pipeline architecture. So the RSIC pipeline, which stands for Automatic Remote Sensing Image Captioning, represents a major breakthrough in automating the generation of descriptive captions from satellite images. It works by first using object detection or algorithm to identify key features such as buildings or roads. Then it uses a clustering mechanism like a minimum spanning tree to ground nearby objects that share spatial relationship. This structure represents is passed to a large language model which generates coherent natural language captions. The body of this system is that it reduces manual labeling effort, which is traditionally very time consuming, and create large scale training data sets that help improve model performance. R6 shows how combining spatial reasoning with with large language modeling can produce high quality human like descriptions at scale. Okay, so this slide shows how the DE datasets One of the largest datasets for remote sensing captioning was created. It begins with raw satellite images from detections datasets like DIOR, DOTA, and XView. The images are first divided into smaller tiles for better resolution and fed into a LLM such as QN2.VL32B, which automatically generate descriptive captions for each life. Next, human experts manually verify these captions to ensure correctness, and low quality outputs are filtered out. So the final datasets, known as DE datasets, and contains over 260,000 high quality localized captions covering 25 objects classes. So this dataset is a cornerstone for training and benchmarking multimodal that operate on remote sensing imaginary. Here we move from static captioning to dynamic reasoning LLM based agent. So this system act as intelligent assistants that can interpret natural language queries about Earth data and performing multi-step reasoning. When a user asks a question like what is the average temperature anomaly in Africa last year, the LLM agents decide which tools to use. For example, connecting to Google Earth Engine API. It generates codes, execute it, interpret the result, and then present the answer in natural language. Importantly, these agents can handle error recovery. If a script fails, the LLM revises it and reruns it. This architecture represents the next generation of scientific computing, where models can understand the question and autonomously perform the analysis. Now moving to the next slide, which is called key datasets and benchmarks. So the development of reliable LLMs for Earth observation depends heavily on high quality datasets and benchmarks. Earlier datasets like RSICD, Sydney captions, and UCM captions provided only general scene level captions. However, they lacked details, spatial, and semantic context. The DE datasets improved upon this by focusing on localized captions with specific objects level detail. Another major contribution is Univ Earth, a measure designed to evaluate the reasoning ability of LLM agents using Earth observation data. It consists of hundreds of true, false, and open ended questions across multiple sensor, tasks, and topics. Together, these datasets form the backbone of training, fine tuning, and evaluating multimodal Earth observation models. Uh, in evaluating these models, both linguistic and semantic metrics are important. Traditional metrics like Blue Rouge and CIDER measure grammatical fluency and similarity to reference captions. But in geospatial context, we also need factual correctness. For example, the difference between a river and road matters significantly. So newer evaluation frameworks which attribute level checks and even LLM as a judge system, where one LLM evaluates another's outputs. The DE benchmark provides a more holistic way to measure caption quality by combining these different metrics, and this ensures that models are not only linguistically sound but also significantly accurate. Okay. Despite the impressive progress, there are still challenges. First, there's a significant domain gap between natural images, which most LLMs are trained on, and top down satellite images. Second, spatial and scale variations make it difficult to generalize. The same object can look completely different depending on resolution. And the third, which is the most model lacks robust temporal reasoning. They struggle to understand how features change over time. And lastly, factual verification is a persistent problem. Uh, Fluent captions might sound correct but describe inaccurate details. Addressing these issues will be key to creating reliable and trustworthy geospatial AI system. Looking forward, the future several exciting directions are emerging. Researchers are developing native foundation Models are pre-trained directly on geospatial datasets instead of natural images. We also need to expand multimodal datasets that combine satellite imagery with geographic, textual, and climate information. Improving spatial temporal reasoning and embedding ethical safeguards into this system is another critical step. Ultimately, the goal is to create models that are explainable, fair, and robust, ensuring that their insight can be trusted by scientists, policymakers, and the public alike. In conclusion, large language models have opened up a new era in geospatial intelligence. They have the potential to make Earth observation data more understandable and more accessible to everyone, from researchers to farmers and city planners. But beyond the technology, this work highlights the importance of collaboration between AI developers and domain scientists who truly understand the Earth system. The real vision is not just build smart models, but to develop reasoning partners, AI system that can integrate data, explain their logic, and support human decision making responsibly. If achieved, this synergy could transform how we monitor, manage, and ultimately protect our planet. Thank you.